Today, as part of this under the bonnet sort of detailed TensorFlow coding activity, I thought it would be wise to have a look at residual neural networks. Okay. Now, just like before, I'm expecting that you would know about what residual neural networks are, or more or less have an idea of what the idea is. But just to quickly give you a sort of an idea. So like usually we would have, let's say, a convolution, a max pooling, convolution, max pooling, convolution, max pooling. Let's say a typical CNN, let's say network, okay? And then you have flattening, then you got your dense layers, yeah, typically. So the idea of residual neural networks or residual network is that, just have this in mind. So what if we come and we add uh, a round of convolution and, for example, max pooling here in between, okay? And then, usually you have the flow of the data that goes in this direction usually, isn't it? So that's the flow of our data into this direction. So what if, while we are doing that, we can have in parallel a residual block, yeah? Now by block, I mean the main code is a block, isn't it? So the residual block, what I mean is just basically a small sort of uh, layer of sort of convolutions and max pooling, let's say, okay? And we put this in parallel to that. And what we do while we are passing our data through, we are also doing this. Yeah, for example, from this point, while the data is going to its usual route, yeah, while it is going down this way, okay, while it is going down this way, we also bypass it and pass it to this residual block, okay? So, sorry, if I do, for example, that, yeah, just think of something like this, okay? So this is going to be called the residual block, yeah? Residual block. And this is your main block of code, main block of, I don't know, convolutional steps or whatever you name it. Okay, so that's the main block and that's the residual block. So models such as ResNet, okay, would have a structure that resembles this. Obviously, this is really oversimplified, but we are going to go simple, isn't it? As you know, I'm not making anything complicated, and I just want you to grasp the idea at the moment, okay? So we'll be making something like this, okay? So let's put the talk aside and see what we're gonna do. So just one thing. So logically, I'm sure now you're happy with writing a code for this, yeah? So you have no problem writing a code for a main block. You've been doing it all along. The idea is that you just have to write a bit of code that would resemble what the residual block is. And then when you write in the main code, you need to integrate this into your main body of code so that you create this bypass. So now we're going to see it in practice, okay? So shall I call this simple residual network? A very simple residual network, okay? And I think it's best if I runtime, change runtime type, and let's go with save, okay? Okay, doc, let's get our hands dirty then. So let's import the necessary libraries. Import numpy as np, import matplotlib dot pyplot as plt import TensorFlow as tf, and maybe we can go and like import the necessary libraries on time so it would make a better sense for you. So let's just have that. Now, we are going to be working, making a model that we will sort of play with it with the MNIST data set, okay? But so we will import MNIST as well from Keras, basically. But for the moment, let's just focus on making the block, okay? So the first thing we're going to do, I know I told you that this is the main body of the code, and then we incorporate this into it, okay? So really, when you want to code out, rather than starting to write the code for this section, you start writing the code for this section first, so that then you can incorporate it into that, okay? So the first bit of code we write is for this, and then when we write the code for that, we integrate this into it, okay? So let's say define, and I'm going to be using the functional API, yeah? Define residual block. Okay, so this is going to be a residual block. It's going to take this input of whatever. Then we're going to define some filters, okay, and a kernel size in it. Kernel size. Okay, doke. So that's that. Now, the input that comes into this is a shortcut, isn't it? I'm saying the input that comes to it, it's like a shortcut, from this point to this point. Let's just call it shortcut, all right? So the input that comes to this residual block is like a shortcut, all right? So why don't we say shortcut? Obviously, you can name it Mickey Mouse if you like, but shortcut is a nice name. Shortcut equals X. So right away, the input that has come into the model, we assign it to the name shortcut. Now, the path of this residual network, okay? So let's start with the convolution. So we're going to say X equals, so actually, my bad. I think let's import the necessary stuff for these neural nets, yeah, CNNs. So from TensorFlow dot keras dot layers import command import input conv2d and add. You will know why I'm using add here. Probably I haven't seen add before with this. Activation, dense, and let's use global average pooling. Global average pooling 2D, yeah, which is just like a flattening, yeah. Well, it's not quite flattening, but it's, I mean, we have covered this before, so I expect, so input, what do I do wrong? Or input. I think I will never learn this. I always make this mistake and I keep using the small I for that. Okay, X equals conv2d. We're going to need some filters, and we have already defined it as a parameter to be taken in by the, with the function that we write in. The kernel size equals, just let's say kernel size. kernel size equals kernel size, and most importantly, padding equals same. Okay, so we want to maintain the shape of the, after the convolution, we don't want it to sort of change shape. Now, what are we going to be feeding into this guy? We're going to be feeding x, yeah? Okay, so we're going to be feeding this x, this input into this. You might be like, okay, why did you call it shortcut then? Well, we'll get to that. But for the moment, just take my word with it. At the moment, shortcut and x are the same. So up to this point, shortcut and x are the same. So the x that I'm giving to this is just same as shortcut. But the moment that you pass this, the shortcut and x are not the same anymore. Shortcut remains whatever it is, whereas x is now getting fed into this layer, and it's reassigned to, whatever is the output. Now let's add an activation function. So x equals activation, obviously relu, relu. And what do we feed into it? Obviously this x. So now this x goes into that. Remember guys, this is just our residual block here. So just a reminder, we are making this part at the moment. Okay, so I got that. Let's add another conv to the x equals conv to d. Then we're going to add filters, kernel size equals kernel size. Okay, again, padding is the same. And what do we feed into this? Obviously, x. Yeah. Now, this is the hot bit, the cool bit. So as I said, we have an input that goes into this, which is x. We assign it as shortcut. Okay. Then when we go further down the line, we're using x and we are updating x. So x is no longer the shortcut. But what do we do here at this stage? We're going to say x equals add. Okay, add what? Well, what we add to it is the shortcut, or the x and the shortcut. Okay, so by summing the output, so we're getting this shortcut, think of it like this, we're getting this data, this x, passing it through this loop, keep our original copy of it. When it goes through these sort of functions, then we add these two matrices together. Okay, so that's what we just did. And let's add an activation for it as well. So x equals activation, and then that's relu, and that is x. And what do we want to be returned? Return x. Okay, there we go. Hopefully no errors. So that's the code for residual model sort of part of the code. Now let's go and make the main body. Yeah. So now we're going to make the code for this section. Okay, for this section. So we've done this, we put it on the side. Now we're going to be using this. We're going to be making this. All right. So now it's just like, as you usually make a run a code in like a convolutional neural network. So you just say input layer or input or whatever equals input, and shape. Said we're going to do mnist, so shape is going to be 28 by 28 by 1, so black and white images. Right, so that's our input. Then we're gonna add a convolution layer, so conv1 equals conv2d, let's say 64 filters, okay, a kernel size equals 7, okay, 7 by 7 sort of padding equals same. And what do we feed into this? Obviously our input. I don't like input layer. I don't put input layers, I put input. Yeah, that's better. So input or input data equals input shape. Then we feed the convolution layer, then we just feed that into this con layer. Okay, so that's our first con. Let's add activation to it. Activation equals, oh, sorry, x equals activation. And what do we activate it with? Value. All right, so that's our activation. What do we feed into this? For conv1. Okay, maybe is it nicer if I do that? Better spacing. Okay, so let's now, yeah, just to keep it simple, do you know what? Now I'm going to add this residual block, yeah? So as I said, that, I mean, ignore the number of layers and the stuff you see here. The idea is that we just made our input, we did something, we are now going to create this connection in between. And already we have prepared the code for it, yeah? So how are we going to do it? I'm going to say, no idea where I did that. I'm going to say x equals, what do we call our function? Residual block. Residual block. Okay. If we add this residual block, what does the residual block take in? Filters and kernel size, because it's going to be using them in, making these layers. Residual block, and we're going to feed x into it. Guys, just bear in mind, yeah, I will explain it in a second. So unlike these that we give the x, the input in a parenthesis at the very end, this is our own function, and our own function is taking the input here, okay? So we're giving that input, this x is now getting fed into that, and let's say filters 64, magic number, and kernel size, now you're gonna like this, because 1, okay? I really want you to go and think about this. I'm not going to emphasize too much on this, but bear in mind that when you use a kernel size of 1 to do a convolution, okay, what is the shape of your output? Yeah, it's going to be the same, isn't it? Think about it, yeah. But then I don't want to confuse you too much at the moment why I'm using this, but just bear in mind that if you do a one sort of kernel of size 1 convolution, well, you get the same output in terms of size. Okay, so that's our residual block initiated or integrated into this. So what do we do next? Then suddenly we're going to say x equal global average pooling, okay, And we go back to our method of functional API, data input. So then X goes here. So here, once again, I did not do this because this is our own function. We have built this and we know where stuff are going, yeah? So that's why you don't have that X here. It's not part of this functional API flowchart. We created this residual block and we integrated it into it. And it takes its input here. All right, we do a global average pooling, which is just like flattening, yeah, but a bit more involved. And then, so if it's M needs, we need 10 outputs, right? Let's just go to our output layer. This is like a really simple residual neural network. So output layer, shall we call it? Or output, let's just say. Input and output, that's much cooler. We need a dense layer. Did I import dense? I did, didn't I? Yeah. Oh, yeah, I did. Yes, yeah. Well, the fact that it's coming means, right. So if it's 10 items, M list, numbers from 0 to 9. So we're gonna have 10 outputs, and we're gonna do activation equals softmax. If it was binary, we would be doing sigmoid, but since it's multi-categorical, we do that softmax. And then what do we feed into it? X. All right. So up to this point, okay, we have our model basically started. Yeah. So we defined this bit, the residual block. Then we wrote a code and we integrated the residual block that we had defined before into it. Okay, cool. Now our final model is what? Model equals model, and I've imported model, haven't I? Okay. I need to import that. Yeah. So I'm going to do it here so that, as I said, you would see where all of these basically usually get used. So from where was it? From TensorFlow dot keras dot models. Yeah. Import model. Okay, so now I can say model equals model and inputs equals, what does the model take? Let's look at it. It takes inputs and an output, yeah? So input is going to be input and outputs equals output. Okay, yeah, that's about it. Hopefully no error. Yes, there is a name activation is not defined. Name activation. You see? Activation. Do we have any? No, that's the only activations, isn't it? Yeah. And name activation is not defined. Residual. There we go. Just pay attention, guys. You see, sometimes you get errors like this. Name activation is not defined, and you're like, oh, okay. Well, where is activation? It's your residual block. It means in your residual block, you have some activation, yeah, something named activation that does not exist. So then you go back up here and you realize that Ali has made this spelling mistake. But I think that should be it. Okay. And then name X is not. Oh, why did I do that? I've put a capital X here. I'm so glad actually that I'm making these clumsy mistakes because I guess you guys are probably catching me and saying, oh, Ali, go and correct that. But yeah. I always make a lot of mistakes with this capital and lowercase, but I'm sure you guys won't do it. Okie doke. So we made a model. Now, obviously, this was just a rough idea for you to get a hang of what this is sort of you're trying to make. So let's go and actually visualize it. Yeah. Let's go and visualize this model. So I'm going to say from tensorflow.keras.utils import plot model. Okay. And what are we going to plot? We're going to be plotting the model. So plot model, model. Let's see. There we go. Okay. So you see what's happening now, guys. Yeah. Let me reduce the size for a second. So, okay. So we defined an input layer that takes in the data, which then feeds it into a convolutional layer. Okay. And then we have an activation. I wish I could actually show this next to the code. I'm going to actually reduce this. Okay. So look at this, yeah. Very, very simple residual model. So we have an input, it's here. We have a conv to the application, which is this, and it's here. We are adding an activation, which is here. Then we have a residual block. Okay, then we have a residual block. What is a residual block doing? Yeah, so this is a residual block. It took an input, right? It took an input that we named it the shortcut. Okay, and then this shortcut, yeah, this shortcut, we kept it, we named it as X. Okay, well, the input I know was X, but like we sort of copied the input, called one shortcut and called one X. With the X, we fed it into the residual, and with the shortcut, we are just passing it along. Okay, so we kept this shortcut here, and we passed the X along. Okay, we kept passing this X along through what? Let's look at it. A conv2d, and then an activation, and then another conv2d. Okay, and then what do we do at the end? We use the add function. Okay, we are adding what to what? The X that got processed through this residual block, and the copy of the X that we named it shortcut and kept it for this point. Yeah. So we are not adding them together. And after we have added them together, we apply an activation function to it, which you can see it here. And now we then have this output basically called X. We are returning X. Then we're going back to our main code. So this was our residual. Okay. Then we have a global average pooling, which you can see it there. And then we have a dense layer with 10 outputs, okay, which is this last one, okay. I hope this made sense. If not, rewind the video and listen, because I think I explained it as clear as I could, okay, what this residual idea is all about. Because for you to go and suddenly, I mean, I see videos on YouTube where people come and try to explain ResNet, and I don't know why would you do that before, having the person sort of fully understand what this residual, adding is, yeah, especially for people like me who learn really slow. So I'm sure all of you learn faster than me, but I'm basically making these videos to help mainly people just like myself who takes their time to sort of understand things. So I try to make them simple. So that's what the residual block is, as I just went through the code. Okay, so nothing complicated. Obviously, when this becomes bigger and bigger and bigger, then it becomes looks more sophisticated and complex, but it's not really if you understand what you're doing in between here. Okay. Ooh, okie dokie. Now, what do we need to do, guys? Let me revert back to the large size so you can have a nice view of it. All right. So now we want to play about with your model, isn't it? I mean, after all, we make it so that we can, have fun with it. So what we're going to need, let's use the MNIST dataset. So from TensorFlow, from TensorFlow.keras.datasets import MNIST, and then we're going to say x train, y train, y train, and x test, and y test equals, what do we say? MNIST.load, isn't it? Let me just look it up. Oh yeah, MNIST.load. It's amazing that I never tend to sort of memorize these things and always have to look at them. Yeah, I think so. Okay, let's quickly take a look at our x test shape. You see, I don't use the capital letter there, and then for some reason automatically by default I put here y test shape. Okay, that's what they are, right? Okay, so firstly, this shape needs to be changed so that we can, feed it to our TensorFlow model. And obviously we need to convert this into categorical. So if I show you y test, it's 7211 blah blah blah. So that's not the right way of doing it. Okay. So we need to make sure that we fit this, we process this correctly. So to start with, let's expand the dimension of this. So you can do either a reshape and just add a 1 at the end, or you can go professional and you can say, I'm going to use capital letter now, actually. Yeah? So I'm going to say x train equals np.expand themes, isn't it? Expand themes, yeah. And we're going to give x train to it, and we're going to say axis equals, well, the last one, okay. And x test equals np dot expand dims, and we're going to feed to this small x test, and axis equals -1. Yep. So let's see. Okay, doke. So far, I didn't do x test. I should do x train here. X test. Okay, doke. So that seems to be okay. So we got the 10,000, which is now 2021, and then 60,000, 2021. Obviously, we haven't done anything with y yet. Now with y, we're going to convert it into categorical. Yeah, so converting y into categorical. Now that we do that, we're going to say from TensorFlow.keras.utils import to categorical. Okay, once we import to categorical, then we can say y So we do this capital. So it's not really what people do, but let's just do it. Y train equals 2 categorical and y train, and y test equals 2 categorical, and that's y test. What did I miss? Oh yes, 10. To give, yeah, because remember this function. Okay, so if I do that, see, number of classes. Yeah, so you give your data and you say that how many classes you want to, and it already does it at the float 32. So if I do my just y test, it's no longer like this if I'm capital Y, yeah. So it's going to be one hot encoded, not categorically encoded, right? All right, so we looked after that as well. All right, what else do we need to do? We are going to start compiling a model. So we have a model. This is a model. Let's compile it. Okay, so let's compile our model. And then we're going to say model dot compile, and then we're going to say optimizer equals TensorFlow dot keras dot optimizer dot Adam, and then learning rate of, I don't know, 0.01, yeah. And then what is going to be our loss? It's going to be, our loss is going to be categorical cross entropy, categorical cross entropy, and our metrics are going to be accuracy. Okay, and yeah, let's do that. So we compiled our model. All right, we are ready to fit the model now. So let's define a batch size. Batch size equals 30, and epochs. You're gonna maybe kill me if I tell you this, but I thought like I first do a epoch. Let's just do epochs of epochs. I don't know, 10. Okay, right. Epochs of 10. Now we're ready to go. So model dot fit, and we're gonna fit it with our x train, y train, byte size of byte size, and epochs equals epochs. Okay, so we're ready to go. I think so. Well, hopefully we don't get any errors. Hey, I didn't make an error. Good. Do you know what? What I wanted to do was also to measure how long it's taking, but all right, we can do that later. Okay, so I just fast forwarded, to factor so you guys don't get bored. So we have now fitted our model, and let's see. Yeah, obviously it's gone to accuracy of 0.97. I've run, like MNIST previously before with you just on a normal convolutional neural network, but the idea was to show you how you go by and use a residual neural network model basically to do the same thing, and we just did it now. So this is taking a bit of time, and then shall we say y pred equals model dot predict x test. So now we have made a prediction. Okay, so we have our white preds and how accurate. I mean, like we can see how the model has performed, but this is on training data. Shall we do let me just quickly do that. All right, so just to save time, basically I've intended this. So we imported accuracy score, and then our white pred shape, just remember it's 10,000 sort of rows and 10 columns. Yeah, 10,000 rows, 10 columns. NP argmax, the y-preds across the columns, okay? So which column has the highest value? Don't do np.argmax just y-preds, all right? You don't do that. It's across its column axis, basically. So it gives you an array, like a number. And y-test is obviously the real data, so 7, just do the same thing. So accuracy of score, I'm just putting this, and I'm putting that. No, sorry, I'm putting that, and I'm putting that, and we get our accuracy score that comes out basically here. I mean, that really is about it. I mean, I didn't think that I want to make this any more complicated than what it is at the moment. Maybe I expand on this on a second video. So I'm gonna name this part 1, okay? And I think that I would give a part 2 to this as well, but that would be on a later date, okay? So, well, as usual, I hope you have enjoyed this. You know what? Well, let's just make it a 1-hour video. So why don't I also show you how we can use a TensorFlow pipeline as well, since I've been showing you how to use pipelines, basically. Let me see. So it just basically means that we're going to give a more efficient structure to our data. So if we want to use TensorFlow pipeline for data, what do we do? Okay, so we're going to say train data equals TensorFlow.data.data set, and then dot from tensor slices. Okay, and obviously what we are going to give to this is x train and y train. Okay, that is going to create our training data, and test data equals TensorFlow.data.data set dot from tensor slices. That's going to be our x test and y test. Okay. Uh, yeah, I think that's fine. Actually, we could do also training data, yeah. Why don't we also do let's do a batching as well, right? Let's do testing. Wow. Okay. We can always, of course, do a train data equals train data, train data equals train data dot batch. Batch 30 and test data equals test data dot batch 30. Okay, so we can always do this as well. All right. All right, that's fine. So now we have our train test data like this. We can now basically go and do, I don't know, I mean, like if it would make that much of a difference, to be honest with you, in terms of efficiency, but why not? You can also say some model dot, our model is already trained though, yeah, so don't care about the accuracy so much. So remember, the model is already sort of trained on the results, but I'm just trying to show you how to use this model. Okay, I'm going to actually reset that. So model that fit train, where is it? Train data, and we have already defined the batches. So, and then we're going to say epochs equals 5, right? So train the model that fit train data, and let's do that. Just for 5 epochs. I should have really timed the other one as well. That would have given us a better indication of which one runs faster, I wonder. Because as I said, like once you got really large data, you tend to have better sort of luck with using the TensorFlow pipeline. But we can actually try it. I mean, as I said, I want to make this a 1-hour video. So let's do that as well for fun. I mean, we have achieved the main objective, which was to show you the residual neural network and how you make it. But this is all extra bonus and fun. So it took about 52 seconds. Okay. So we could do the same thing with this. Epochs equals 5. And byte size is 30. So you just need to, let's see if this does a better sort of timing in epochs 5. Okay. So remember, this is what I just did. Usually fit, compile and fit. I'm just trying to show you the effect. This seems to be running faster actually. So Ali keeps saying that use TensorFlow pipeline, but we haven't seen significant improvement or even any improvement. Obviously, I've shown small data. So, all right, soon we are going to discover possibly almost the same thing. I think this is running a bit faster with the standard. Okay, what's happening? Well, while this is running, I'll just give you a final recap. So guys, a residual block is nothing that significantly super complicated. You're having your main block. Before you make your main block, you define a residual block. Then when you are writing the code for your main body of code, or body with the main block of your sort of model, then you incorporate that functional based model in between. Now, obviously, you can add as many of these, you can make this as long as possible. In fact, this idea was developed to prevent vanishing gradient issue. Yeah, but I'd like you to go and read about it yourself. Yeah, the idea was to have these residual block in between, so that during the back propagation, you won't get so much, you know, gradient decay, and sort of, like having minuscule values during the back propagation for the gradients. But yeah, this is a very simple residual block. So I'd like you to go and explore ResNet now. So knowing this, go and try to see if you understand the structure of the ResNet. Okay, and this took 1 minute 22 seconds. Oh wow. I just wonder if that was some form of a glitch, or I'm just gonna run it. I'm going to fast forward it for you. Okay, so yeah, I think that probably was due to some server or something like that. Okay, it's about 45 seconds, which is not typical, not better than actually the other one. 2 seconds, but yeah, that's about it. Okay, well, I hope you have enjoyed, experiencing the first taste of what this ResNet is all about, and see you in the next lecture. Bye.